Hi, thanks for joining me. Today's video is going to be slightly different. I've got a false proof video. I've made a couple of these before, but I thought I'd do another one today in which I claim something is true, and in this case it's something really absurd, and I'm going to prove it, but there's going to be a big flaw in my proof, and I want to see if you can spot it. And in fact, in today's one, the flaw might be a bit more subtle, but let's see if you can spot it. Anyway, this is the claim that I have, which I will prove in just a second. I claim that 2 to the n equals 1 for every non-negative integer n. Okay, so when n is 0, 1, 2, 3, and so on, if I do 2 to the n, I'm always going to get 1. Now, of course, this is bogus. This is clearly not true. If I just look at the case n equals 1, 2 to the 1 is 2, which is definitely not 1. And in fact, for n bigger than or equal to 1, 2 to the n is bigger than or equal to 2, and thus definitely not equal to 1. Okay, but I'm going to prove that this statement holds and see if you can spot the flaw. Okay, so the way I'm going to prove this is by induction. Let's look at the base case. So that's the case n equals 0, and then, well, we certainly have that 2 to the n is 2 to the 0, which is 1. Okay, hopefully there's no arguments in that line there. So the base case holds true nice and well. Now what we're going to do is sort of proceed by strong induction. So assume the result holds. Assume 2 to the n equals 1, and that's for all n up to some number k, where k is a non-negative integer. Now we're going to look at the case 2 to the k plus 1. Okay, well 2 to the k plus 1, I'm going to write it in a bit of a weird way, but I'm going to write it as 2 to the k times 2 to the k all over 2 to the k minus 1. Now firstly, let's check that this is indeed the same thing as this. Well, let's look at the numerator. If we bring these two together, I get 2 to the 2k at the top, and then I can subtract the exponent, so I've got 2 to the 2k minus k minus 1. So this thing here is the same as 2 to the 2k minus k minus 1. And of course this thing here, if I do 2k minus k, that's k, and then I do k minus minus 1, which is k plus 1, I get the k plus 1 there. So this does in fact equal this thing here. But then I can apply my inductive argument, my assumption, because I know that 2 to the n equals 1 for all of these things here. So when n is k, because k is clearly in this set here, this thing here is going to be 1. Then I get times another 1. And on the bottom I've got k minus 1, and clearly k minus 1 is in this set as well. So we get 2 to the k minus 1 is also 1. So we get 1 times 1 divided by 1, and that of course is just 1. Okay, and then that means that 2 to the k plus 1 is 1, and then that ends our proof by strong induction. Okay, so the subtle flaw actually came in just here. It was a bit sneaky, and in fact, as we know, 2 to the 1, so in the case where n equals 1, certainly isn't 1. 2 to the 1 is 2, which is definitely not 1. So there's got to be something that messes up at the very start of when we try to apply our inductive argument, and in fact that occurs right here. We said that 2 to the k times 2 to the k is 1, and in fact it is because of this thing here. However, I said that k minus 1 is clearly in this set here. But we can see if we look at the case where k equals 0, i.e. the very first case, the base case, k minus 1 is not in this set. And thus we can't just say that 2 to the k minus 1 is 1. Now of course, if k were bigger than 1, then k minus 1 would certainly be in this set here. But we've got to ensure that k minus 1 is always in this set for any value of k, especially, and in particular the case k equals 0. But if k equals 0, this set here is just the set with just 0 in. And of course then k minus 1 is minus 1, which is definitely not in that set. And thus we can't apply our assumption in this step here, and thus we can't make this conclusion here. And that's where the flaw of this proof is. But yeah, I hope you have enjoyed this video. The main reason I made this video was firstly do something different, but also to highlight the importance of taking care, especially in inductive arguments. Sometimes you can fail right at the start in a sort of subtle way, which you think would hold for all integers. So in this case, this set here, 0, 1, 2, all the way up to k, but you've got to check just the small cases as well. There's a very famous example in which you prove, I think it's all horses are the same colour, or prove that every single person on the planet is the same height, using a sort of inductive argument. But it's the flaw in that proof is right at the start in the one of the base cases. Anyway, I'm waffling now. I hope you have enjoyed this video. If you are new here, please do consider subscribing and checking out some of my other fun maths videos as well. But that's all for now. I will catch you in the next one. Have a great day.